Welcome to Spring LIB.
Okay. In this problem, we're asked to find the de Broglie wavelength for a relativistic electron with two different velocities, one that's about half the speed of light and one that's close to the speed of light. The two equations that we'll need is the definition for de Broglie wavelength for a particle with mass. This is h, the Planck constant, over p, the momentum. And we can use the relativistic momentum for a particle with mass, which is mc root gamma squared minus 1. And recall that gamma is the Lorentz factor, and it's defined as 1 minus v squared over c squared, all to the negative 1/2 power. And this determines the strength of relativistic effects for a particle that's moving at a speed. All right, so let's jump into it. So to start off, we can get our definition for de Broglie wavelength, h over p. We can plug in a relativistic momentum into this expression, and we are left with h over mc gamma squared minus 1 all to the 1/2 power. It's a square root. And we can solve for gamma before we solve for this entire expression. So in part A, gamma is simply 1 minus 0.48 c squared over c squared, all to negative 1/2, which gives us 0.52 to the negative 1/2. And we can just simply plug in that number. And we could use, for h over mc, we can say 6.626 times 10 to the negative 34 joule seconds, all over the mass of the electron, which is 9.1 times 10 to the negative 31 kilograms. Speed of light is 3 times 10 to the 8 meters per second. So that's all. These are all constants. And then we can plug in our value for gamma for speed in part A and part B separately, and calculate for lambda in both cases. For part A, we will obtain a lambda of 4.43 times 10 to the negative 12 meters. And for part B, we will obtain a lambda equal to 7.07 10 to the negative 13. So as our particle got faster, its wavelength, de Broglie wavelength, went down. And just worth noting, at least for part A, if we compared this relativistic expression to the non-relativistic version, we would get a bit of error, because the non-relativistic version would be about 5.05 10 to the negative 12. So it's not that bad, but it's something. And if we did it for part B, we would have a much bigger error as well. So that's why we need to use a relativistic expression to get a more correct answer. Anyway, that's it. These are the results. This is the sample calculation. Thank you very much.